Alrighty, my lovelies. Shall we do some science?
Yeah.
Yeah? Okay. What shall we do?
I don't know.
Okay, well, I've already got an idea, don't I? That's why I got the stuff out already, hey? We have some vinegar and we have some baking soda. This is the same stuff we used the other day, isn't it, guys, to make the rocket?
Yeah.
Yeah.
But this time, we brought a spoon for this.
That's right, we did bring a spoon. What we're going to look at, guys, is something called rate of reaction. Okay, this is chemical kinetics. Kinetics is about how fast reactions proceed, okay? So we know that the sodium bicarbonate, the baking soda, is going to react with the vinegar, don't we? Because we saw that with the rocket, hey?
Yeah.
Yeah, well, we're going to do it again, okay? But we're going to do it in these containers, right?
Yeah.
So we know what's going to happen. Who remembers what is going to happen?
It might blow up.
Well, it would blow up maybe if there was a lid on the container, but there's no lid. What are we going to make?
It's gonna make bubbles.
It's going to make bubbles, that's right.
Oh, yeah.
Okay, so what we're going to look at is which one is going to make bubbles the quickest, or the most bubbles, or the quickest and the most bubbles. Okay? And that reaction, we say, proceeds more readily. Okay? So, first up, what we need to do, Ken, can you get the vinegar and put a little bit of vinegar, yeah, in this bottle, just here, yep. And so take off the lid. Now, can you pour that, or do you need Alice to help? Okay. Ken, maybe you hold the cup, eh? Ken, you hold the cup? No, the cup. Yeah, just one of them. Yeah, right. You hold it there, and Alice can pour in just a little bit of vinegar, okay? We don't need too much. Oh, okay, more than that. Okay, pour. I'll say when. When I say not too much, I mean actually do put some in. More. Bit more. Yeah, stop. Whoa. Okay, that's a really good amount actually. Now the thing is, I want the same amount. No, don't close it. The same amount in the other cup. Okay. Here's something about science, guys. When you're doing an experiment, you only change one thing. Okay. Okay. So we're not going to change how much vinegar we use. All right. So that's why we need to put the same amount into each cup. All right. Go.
Tell me when to start.
Well, make it the same as the other cup.
So you know how.
That's good thinking, Ken. That's good thinking to put them next to each other so we can see when they've got the same amount. Bit more. Bit more. Bit more. Bit more. I reckon stop about there. Stop. Lovely. Right, put the lid on the vinegar.
That's the same height.
That is, isn't it?
Yeah.
Alright, skis. Now, we want some of that baking soda into each container. So let's start with one. No, not into the vinegar, not into the cups, into these long containers. Sorry. Yep.
Wait, both?
Yep. So let's start with 1 spoon of it. I'll just move these vinegars out of the way. Yep, you can do it. 1 spoon. Yep. Okay, so put that in. Good job. And maybe 1 more of those, because that was like a half spoon, so we'll put another one. Perfect. Hey, just tip the container so you can... There we go. Alright, now we want to do that into the water as well, Ken. So the same amount, okay? Because we're not changing the vinegar, so we had to put the same amount into the cups.
Like this?
Yep. And then another one of those. And we're not changing how much baking soda, so we need to put the same amount into each container, alright? Because those are the things that we're not changing. Hey.
Yeah.
Now, guys, the things that we're not changing, perfect, Ken. Drop it in. The things that we're not changing has a special name. It's called the controls. Okay? We're controlling how much those we're not changing, so they're the controlled variables, okay? So far, so good. Now, the baking soda that went into the water, Alish, oh, we probably should have mentioned that's just water in that one, isn't it?
Yeah.
Just water from the cold tap. Can you swirl that around a bit? We want to dissolve it all. Good job. Right, can you see any of the white powder looking stuff at the bottom? Yeah? Right, can I just have this for a sec? Thanks. Because we all want it to all dissolve.
Because then the spoon would just go over.
I know, the container's too long, isn't it?
Yeah.
Yeah. But there we go, we've dissolved the baking soda, okay?
Yeah.
Cool. Let's put that one in front of you and this one in front of you, Ken. All right. The baking soda out of the way. All right. Who wants the pink cup?
Me.
Okay. Yep. Give that to Ken. You take the purple one, Alice. What's that? Oh, now here's the thing. We're going to pour them in at the same time. Okay. So hang on. Just moving these things off the table.
Yeah.
Spoon doesn't matter. Now, at the same time, can you pour yours into your container and Alice, you pour yours into your container? Are you ready? Shall we have a countdown? 3, 2, 1, go. That's a perfect result.
That one went quicker.
It did, didn't it?
Yeah.
Now, Alice, just watch out because that's about to run off the table. Excellent result, guys. So, which one went quicker?
That.
Alish's side, right?
Yeah.
That's the one that had the baking soda dissolved in water.
Yeah.
Isn't it? And it went quicker. Do you know why it went quicker?
Why?
Because it was dissolved. Instead of sodium bicarbonate, we had sodium ions, and we had bicarbonate ions.
Yeah.
And because it had already broken apart, that meant it could react with the vinegar even quicker. Okay?
Can I touch this?
Yeah, you can. You just have to wash your hands after. Was that good fun, guys?
Yeah.
Cool. All right, let's have a quick look at what was actually going on in terms of the science. Why did one go quicker than the other? Well, here's the reaction equation for the chemical reaction we just saw. Sodium hydrogen carbonate, better known as sodium bicarbonate, more commonly known around the home as baking soda, is one of the reactants. So we've got baking soda, sodium bicarbonate, and we had vinegar. Now, vinegar is acetic acid, also known as ethanoic acid. Actually, technically known as ethanoic acid. That's its new name. Its old name is acetic acid, but people around the world still use its old name, but that's fine. So we had baking soda, sodium bicarbonate, and we had vinegar, acetic acid, and we made three things. We made sodium acetate, this stuff here, or using the newer name. Technically, it's sodium ethanoate, but sodium acetate's fine. And we made water, and we made CO2. Now, what we actually looked at was the rate at which we made CO2. CO2, of course, is a gas. That's why we had all those bubbles forming. Right, so we've started putting in states. Let's do that. Vinegar, like I said, is acetic acid. Any acid you ever get is in aqueous solution, which means it's been dissolved in water. Right, aqueous, or watery. The baking soda. Let's do Ken's version first. That was a solid, and we made some water. That was a liquid, and some sodium acetate. That was actually an aqueous solution as well. Okay. So there's our reaction equation with states shown. Remember, aqueous, it's not a state of matter. When we say show your states in your reaction equation, we just mean solid, liquid, gas, or aqueous. We're not talking specifically actual states of matter. So that's what we had going on. Now, this was a metathesis reaction, also known as a double displacement reaction. Vinegar, being an acid, donates a proton, which is a hydrogen ion, which is this guy right here. That bugs out as the H+. Now, it needs to hook up with another negative. Okay. Well, here's a negative over here because the hydrogen carbonate ion has a negative charge. Okay. So, you can go away. That hydrogen ion comes over and hooks up with this hydrogen carbonate ion, right, the bicarbonate. And that leaves this poor little sodium out in the cold. It is displaced by the hydrogen ion. But that's okay. Don't feel bad for the sodium because now I don't really have a good way to draw an arrow. That sodium, this guy here, hooks up with this acetate ion. Okay. When the hydrogen ion left as the plus, what was left behind, if we actually make it leave, was negatively charged. Okay. So that hydrogen ion comes and kicks this sodium out of place, so it's not there anymore. Okay. The sodium ion takes its positive charge with it, so that leaves a negative charge for the bicarbonate. That sodium ion, let's just write them in here. That now hooks up with this, the acetate ion. Okay, so what's really happened is the two positively charged ions, the hydrogen and the sodium, have essentially just switched places. Okay, the hydrogen displaced the sodium ion, or the sodium ion displaced the hydrogen ion. Okay, we would generally say that the hydrogen ion displaced the sodium because it came from an acid, and acids are hydrogen ion donors, right? Proton donors. So that's what's going on. And so because two things were displaced, it's a double displacement reaction, also known as a metathesis reaction. All right. Depending on who you talk to, you'll get it called different things: a double displacement or a metathesis. I actually usually call it metathesis. That's how I learned it. But a lot of people commonly call it a double displacement reaction. Cool. So, actually, not so cool, because that doesn't give us our product. Our products are sodium acetate. Yes, we made that when the sodium ion hooked up with the acetate ion. We made sodium acetate. So far, so good. But we don't actually have water and CO2 gas. When that H plus hooks up with the bicarbonate ion, okay, so when we follow this hydrogen ion down this arrow, hooking up with this bicarbonate ion, we're going to get, oh look, there are two H's now instead of one. And the plus and the minus, they will cancel out. So we're going to be left with this. Now this is actually another acid. Okay, this is carbonic acid. It's another weak acid. But the thing about this one is it is fairly unstable. It self-dissociates. So this undergoes a decomposition reaction. Basically, it just breaks apart all by itself. And the C takes off with two of these O's to make our CO2, and that leaves our two hydrogens with the other O to make our water. Okay, so this overall reaction is actually a two-step process. First, we have the metathesis reaction, and then we have a decomposition reaction of the carbonic acid. Okay, cool. So that's what happened with Kien's version. Now, what we have here is Eilish's version. Now, you'll notice I've left the state out for the sodium bicarbonate. Eilish's baking soda was dissolved, so it wasn't a solid like for Kien's version. It was actually an aqueous solution. Now, here's the thing. That is a salt, an ionic salt. Right? Not a salt like it got beat up, but a salt. Right? So in chemistry, we've got this thing called salt. Okay, this is normal table salt, sodium chloride. This is an example of a salt. Okay, because this stuff was made from the sodium ion and the chloride ion. They came together, attracted by those opposite charges, and they hooked up and made this sodium chloride. This is your normal table salt, but it is one example of a salt. In chemistry, the word salt just stands for any ionic compound, okay? It was made from ions. An ion is something with a charge, an atom or a group of atoms with an electrical charge, right? Plus or minus. So because it was made from ions, we call it an ionic compound. And ionic compounds, just for short, we call them salts. So salt, table salt, is an example of a salt, but so is the sodium bicarbonate. Now, when it was dissolved, okay, in water, hence it's aqueous here, we dissolved it in water, we actually didn't have any actual sodium bicarbonate, because when you dissolve a salt, it splits up into its ions. So we had some bicarbonate ion. We also had some sodium ions. Okay. Now, that just made the reaction with the acid quicker, because that sodium didn't have to leave the bicarbonate to then hook up with the acetate ion. Remember, this acid does its good little thing. That hydrogen is gone, donated. It wants to hook up with this bicarbonate. That's fine. That will make carbonic acid, which will then self-dissociate. So that's a decomposition reaction. And that will give us our water and our CO2. But this acetate ion hooks up with the sodium ion to give us sodium acetate. Well, it can do that much more quickly now, because the sodium has already left the bicarbonate, right? Like first the sodium would have to leave the bicarbonate. Now it's free to hook up with the acetate. well, the sodium has already left the bicarbonate. So that's what makes the reaction just that much quicker. Essentially, one step has already been done. Okay, so if you're having to do less steps, it's not going to take as long, is it? Okay, so this is Eilish's version. The sodium ions were already in aqueous solutions. I should write that in. We're already in aqueous solution, ready to hook up with the aqueous acetate ions from the acetic acid. Okay, and so it went quicker. Grand.
Don't forget to hit the like button. Yeah. And subscribe to It's Up Here. And here's another video.